As Sean introduced, I'm Catherine. We have Lynn, Roger, Haley, and Richard with us. So specifications about pressure loss and pipe fittings. So first off, we'll begin talking about the residential energy use that a lot of the studies come from. Moving on into water sense and structural waste. Looking at the plumbing materials used, explaining the equivalent links, and then also letting you all know about the methods of testing that's happening.
And since you have 15 minutes, just keep yourselves on target.
Okay, so this is the third slide.
So moving on, so beginning with the energy use demand, the part that we're looking at is with water heating, and you can see it's a large amount of the demand for energy, and actually from recent years it has gone down, but it's still taking up a significant portion. Much of the data has come from the rec center and came out of the Department of Energy.
So water sense, we're on to the next slide, by the way.
So that the Zoom can hear you guys.
Oh, okay. Oh, I didn't know. Okay. So water sense labels on toilets, showers, and other water fixtures is basically ensures that the product meets EPA standards of energy usage and efficiency. Specific requirements for being a water sense product would be a storage capacity of 0.5 gallons and 0.6 gallons maximum accumulation. And other considerations such as pipe diameter and the presence of the inline fittings, which we're studying, are more or less concerning depending on the type of hot water delivery system. So we're concerned with water sense because we'll be testing for pressure loss in the piping depending on the different fixtures. So that will end up affecting the storage capacity and the accumulation. So the results will indicate if it's within or without the water sense standards.
To tie it together, Sean Orm presents on 3/8 inch plumbing piping. That's really not allowed basically in California. And this research is trying to teach engineers that it's okay for studying it to help them create the new curves so we can move forward.
So one of the reasons that Gary Klein, who we've been working with, raised this issue is because when we talk about pressure loss, engineers talk about major versus minor loss. Major being associated with the friction loss through pipe, and minor losses is kind of just a naming convention that was brought about by when they were designing piping systems initially. It was pretty much large scale. So on the left, you can see there's about 20 fittings for half of a city block, whereas there's about 20, maybe more, in the whole system in just one house. And then next slide, you can see not the best, but a typical hot water distribution system. And this would be one example of one that would be a high structural waste system. The next slide was given last year at the ZNE conference by Troy Sherman, and it shows about how much percentage-wise of the losses can be associated with structural waste versus behavioral waste. This project is more focused on the structural waste side. And so on the next slide, you can see a design of a compact hot water distribution system that would meet the water sense requirements of under half a gallon in the pipe. And now Roger is going to talk about what we're going to be testing in this project.
So the three different types of materials we have. The three different type of materials we're using to test with are copper, PEX, and CPVC piping. We have diameters going from 1/2 inch, 3/4 inch to 1 inch. And we are testing couplings, T's, and elbows. And next slide. So why is PEX and CPVC piping being used? It's relatively cheap to produce compared to copper. It's about 5 times as cheap as copper, and it's easier to install. There's less labor going into that. There's a lower life cycle assessment compared to copper because it takes less energy to produce the pipes. It takes a lot of energy to melt copper. And then the fossil fuel industry is also peddling a lot of money towards plastic piping. And next slide. So in this literature review, I'm writing about the health effects of PEX and CPVC piping. I decided to look into what contaminants are found in water that use these types of piping. And in PEX, there's upwards of 16 different organic molecules found in your water, and 2 of those is toluene and pyridine. Toluene historically has been used in the 1980s in Indy cars for as a race fuel. It's pretty much methane without an extra hydrogen. And then pyridine also, it's pretty much a benzene molecule, but it has nitrogen instead of a carbon and a hydrogen atom, and it's historically been used to denature alcohol, pretty much make it so you can't drink alcohol, and that's in your water. So it's some good stuff. And then contaminants found in water for CPVC, a lot of volatile organic compounds, which are pretty much chemicals that quickly change their phase because they have a low boiling point. There's also total organic carbon, which is a water quality measure. And so the more total organic carbon you have in your water, the lower quality it is. THM formation is as a result of using disinfectants to clean the pipes. And that is, the name for that is trihaloomethane. And it's pretty much just a methane molecule with a halogen replacing a hydrogen. And a commonly known molecule in that category is chloroform. And then also residual disinfectants, it's like chlorine, anything really that can clean your pipes, and a lot of those are carcinogenic. Toluene, there's no evidence within the EPA that it is carcinogenic, but it's gonna come into this cocktail of all these different things that you're exposed to and can very well lead to cancer. And then this is where my literature reviews kind of ended so far, but to take it further, I'm gonna look into instances where these chemicals break regulations, and then also tie in these chemicals, if there's any of these chemicals in the water around the factories that produce these pipings, and not just focus on the end use, the people who are drinking the water. And now Lynn's gonna take over.
Okay, so a big part of what we're doing is testing pipe fittings, as it's been said a couple times. So on the next slide, the way that to make calculations simpler, pipe fittings have their own minor losses, and they are usually represented by an equivalent length to model just straight pipe. And on the right hand side, you can see 4 different fittings, and these are all the same diameter pipe, so they're all 1-inch pipe. But as you can see, the ones on the right hand side look significantly larger than the ones on the left. And the big discrepancy that Gary Klein has brought up is the fact that a lot of these elbow fittings, if they're considered a 1-inch diameter 90-degree elbow, you would have one equivalent length where there should be multiple. So on the next slide, it's the different equivalent lengths for PEX half-inch elbows, 90-degree elbows, and the bigger graph has a lot of numbers that vary. So Viga has a lot. They test all of their different elbows, but as I said before, if you look on the right, there are numbers that are closer to just having one number representing a bunch of different fittings that still fall under a 90-degree elbow. The numbers for CPVC that we found, these are all equivalent lengths for a 90-degree half-inch fitting. So the CPVC one shows you that 1.5 is what's typically used. If you move on to copper, the 1 is usually used to model a copper fitting of a 90-degree elbow. And so the hope for this project is to identify what a method of test to find the equivalent length of 90-degree elbows, and hopefully moving on from that, tees. So if you move to the next slide, it has the desired results. We're going to be measuring the temperature, flow, and pressure, and this is like a preliminary drawing of what we're hoping our measurement rig is going to look like. And so we'll be measuring temperature with our TDs and flow with the flow meter, and then we'll be measuring pressure on both sides of the tests. So these are the condensed equations for what equivalent length is considered. So equivalent lengths are equal to the friction factor, and they're based on friction factor, the K coefficient, and diameter of the pipe. And so using the measurements that we'll be taking, we'll be able to find a friction factor and a K coefficient and be able to measure the length, the diameters of the piping in order to find equivalent lengths for all of those materials. And then that's the end of our presentation.